Hello everybody. Today we understand the semiconductor device manufacturing process. It's not general process description today. It's focused more on the dimension of the transistors and stuff. So it's inevitable to talk about EUV, DUV. It's right now a discussion going in the market. And also much deeper understanding of what the really dimension is and what that dimension affect what density. Talk about density, transistor density on a chip. The is a log scale and year. And one time the Intel's founder, they observe every year the density increase double every 2 years. 2 years, okay, and this is called Moore's law, but it's not a law, and nothing to make this density increase forcibly scientifically. It's just observation. And it's keep going. So question is, we are very close to 3 nanometer. So how long can we go? Think about the silicon's crystal. The distance between the atom is about 0.2 nanometer. So if 2 nanometer, it's about 10 atoms. So if you have a crystal, 10 atoms exposed, and you have this is the MOS channel, only 10 atoms. We started with a band with theory, means crystal make an energy band, and the electron move, hole move this way. This is plus minus kind of theory. Can we apply this theory with such a small domain, only 10 atoms? That's a big question. When it comes to 10 atoms, probably more quantum effect comes in more and more, and it's probably this theory doesn't apply anymore. The crystal energy band created by crystal band is not going to be good enough to describe the behavior of electron and hole around here. So the same way the transistor made in smaller is we're here Moore's law. The either this function as transistor is questionable. Okay, and what is actually transistor dimension they are talking about? So you make MOS in the top view. You put the silicon oxide, right? Oxide of silicon. And you have a width. Typically, when we talk about transistor size width, the width is the size of a transistor, but this length also important in the MOS, right? Remember, the I is related to length over W. Okay, so you want to make both small. The bipolar transistor is much different. You have a P well, and N well is created like this, and that's going to be emitter. The top view. And you have the ditch connected to the bottom collector layer, N layer. So So what is a bipolar transistor size? Actually, this is not the size. The size is only this portion. Okay? So this is a width to determine total current, and this width is the transistor size. And bipolar has the advantage of determining transistor size because you make a small window over P. It's much easier to make a window because window size is the same even there is some misalignment, maybe a little bit this side or a little this side. It doesn't matter. So the bipolar is more accurate as long as transistor characteristic, less variability. That means you can make better analog. Circuit. And MOS is kind of, you try to make this, there is a diffusion. I'm sorry, this is silicon O2, and here you get the N. Let me clean up here. N plus, this is N plus. Since it's diffusion, this penetrate to horizontal direction too. So actually N to N distance is smaller than this the silicon oxide silicon. So are we talking about this when you say 2 nanometers, and or you're talking about this 2 nanometer? This is the channel, but channel inside is because the diffusion goes to the horizontal direction, grows horizontal direction, the actual channel becomes smaller. So which one you're talking about? If it's actual channel, and it's going to be even less than 10 atom for 2 nanometers. I really doubt that there is a transistor effect with less than 10 atoms. But they build thin 3D transistor, FinFET. So it's like they build a MOSFET on top of the silicon, and that's what 3 nanometer method going. So it's not conventional 2-dimensional MOS device. It's a 3-dimensional MOS device right now. And so where the term density come from? The density, even this one is not 4 nanometer. If you push more transistor in within the area, then it's become equivalent to 3 nanometer flat 2-dimensional transistor density. And Moore's law is talking about density. So as long as the density is equivalent to 3 nanometer, although you use a 4 nanometers process, you call that 3 nanometer device. Okay, so this is probably each company uses a different definition of the transistor size, so it's not really reliable. It's just when they talk about 2 nanometer, 3 nanometer, or Apple made a CPU chip with 4 nanometers, which one are you talking about? It's not really TSMC and the Chinese side and Intel. They all has a different definition of the transistor size. Which part you are talking about? The 3 nanometers, 4 nanometers, and so on. So the IBM, the first 3 nanometer device made, but actually it was 4 nanometers process, but because of 3D structure, the density increased to 3 nanometer, 2D 3 nanometer equivalent density. That's what it means. Okay? So when you talk about 3 nanometer, 2 nanometer, it's kind of each company uses different definitions, and meaning is not really the clear. Okay, now when the long time ago there is a wafer and you expose light through mask, and this is wafer, and you expose lights and you create basically silicon oxide. So what happened is the mask expose light here, and they fill with photoresist, right? And only this area is going to be this is opposite. Mask has this one, and the light blocked here, and the light hit photoresist harden this part, right? And you etch away, so you get the silicon oxide that's act as a blocking for diffusion. Diffusion processes, you have a large tube and you put the impurity N plus, the many wafer here, and heat up, and it's a diffusion process. So heats and the gas get into the silicon, and it slowly diffuse this N into this way, N plus, right? Okay, if there is another one, then you put another mask for the metal process. Let's see. And this entire area is going to be filled, right? And you place you have to etch away, so you get you need to have this blocking. I'm sorry, this is always negative. I keep confusing negative and positive. When you photoresist, if it's hit, then dioxide. So you have to have a mask here. Again, the place you want to leave the photoresist is going to be here for the gate. So the mask is going to be here. No. Let's see. You want to leave here, so you have to make an opening for photoresist, and fill with the photoresist. You hit lights, then you get this part, then you put the metal here, the gate, right? So this is drain source. Okay, so it's repeating photoresist and size. Photoresist, the quality of photoresist become very important, because photoresist includes various material, and when you etch away, there is a limit. What is the finest pattern you can etch away? If it's a 4 nanometer, well, probably you can't use the 4 nanometers process. It should be 3 nanometers, because the etching, the edge become like that, right? And this distance and this distance become so different. Okay, so the photoresist quality has to be also improved in order to make a smaller 3 nanometers transistor fine patterns. Now, how about this method? Is they switch many years ago to stepper. What a stepper is? Stepper is each die you have a mask and you expose, and after expose, this window move according to the wafer's geometric shape. Okay, so you expose this each die one by one. This is called a stepper, and that's a EUV stepper and DUV stepper, and the difference is only frequency. The Y frequency is important. The energy of electricity, the light is frequency, and the higher frequency, the light exposed here, it can handle very sharp contrast, higher resolution. So they move from DUV to EUV frequency, and the making a laser for such a high UV light is very difficult for such an area. So stepper, this move little die, mask, and light source together on the wafer and make a die one by one. This is entirely computerized automation process. So of course yield increase. The major motivation was from here to here. Conventional mask method to stepper is yield. The reason is when you have a mask, you have like 20 masks in the process. Each time you align the mask from the previous mask position, and there is an index mark, and you align it and expose the light. This index marking alignment is sometimes slightly off. So wafer is big, then this the distance of the off distance increased, yield decreased. But if you do this method, each die do the alignment, so much better yield. So yield was a main objective to move to stepper. But later, when the transistor size gets smaller, then this stepper becomes very critical, because you need higher intensity lights in a small area. There's no way you can do this entire wafer right now. So stepper move very quick, one by one, on the wafers, and later you scribe. It's a cut by diamond cutter. The wafer is like glass, very brittle. Then take the die out. So each chip can be taken out by robotic hand. So of course after testing. Okay, so as a summary, when you talk about the size of a transistor, this definition is depend on the company. It's all different. They want to talk about density. The density, because even transistor is very small. If minimum metal size is large, then transistor is small, okay, but the density is low because of the restriction on the metal size. You know what I mean? So density affect the die size. Say if you have 100 million transistors, the transistor size is determined by what? The channel size or metal size? It could be photoresist limitation. So that's a density. Transistor size, even density is lower in this case. Transistor is small, so transistor characteristic will be the faster and less power required. But the density cannot be big. So overall technology is necessary. The better quality photoresist process and stepper like EUV, it can handle higher resolution than the DUV. So it's like overall technology is necessary. It's not just EUV and DUV. So that's the semiconductor manufacturing process. It's, the key is photoresist and stepper, and yeah, that's about it. So the general description of there are plenty of books you can read about how you make this diffusion process to drive the impurity into the silicon. And there is a sputtering. Sputtering process is like in the wafer you drive the impurity at a certain energy. So this area is going to be, the diffusion go from surface, but this one just jump into this. So it's because of the energy, it's break a lot of silicon crystal bonding. So after sputtering, you do the annealing process, means you increase the temperature and decrease slowly. Then all the broken bond, the silicon heal. Then you make a nice N plus layer or N layer within the silicon, and you make another one diffusion process this way. So this is typical collector for bipolar transistor. You have a embedded impurity layer. That's typically use sputtering process. So those are all described in books and online. You can read about it, but we just went through the key aspect of semiconductor manufacturing process, like EUV, DUV, and photoresist, and the meaning of density, meaning of transistor. Meaning of transistor doesn't mean the meaning of density. So the that's entire process technology has to be considered to evaluate how good that the process is. Okay. So if you like today's video, please subscribe and check a like and wait for the next video.